Hey guys, welcome back to another video. In this video, we are going to solve some hard questions from the topic thermal physics. That is, it contains thermodynamics, temperature, and ideal gases, right? This is from, again, A2 physics, and we're going to solve around 5 questions in this video. So let's start off with the first one, that is from summer 2021, variant 4.2. So this is question 2 of that paper. What is the question saying? An ideal gas has a volume of 3.1 into 10 to the power of minus 3 meters cubed. Volume, pressure of 8.5 into 10 to the power of 5 pressure, and temperature of 298 Kelvin. This is the initial condition of the ideal gas, right? The gas suddenly expands to a volume of 6.3 into 10 to the power of minus 3. New volume. During the expansion, no thermal energy is transferred. Very important. Del Q is 0. No thermal energy given in, no thermal energy taken out. The final pressure of the gas is 2.7 into 10 to the power of 5. At temperature TF, as shown in figure 2.1, show that the number of gas molecules is 6.6 into 10 to the power of 23. Now, these are the new condition of the ideal gas after being expanded. Pressure has decreased and temperature, you don't know. So, expansion has taken place over here. And no thermal energy put in. Now, you know that the number of particles are not going to change since we're working with the same mole of gas. Now, thereafter you show the number of gas molecules. You know the formula, PV is equals to nRT. You can also write this as PV is equals to nKT, right? So, I'm going to use the easier one. I'm going to use PV is equals to nKT to directly find out my number of particles. Great. So, I know the pressure, I know the volume, and I know the Boltzmann constant that is given in your data sheet, towards the beginning of the paper. And I know the temperature. And I'm going to find out this N, which is capital N, meaning number of particles. If I make N the subject, what I see is N turns out to be 6.58 into 10 to the power of 23. You can calculate it for yourself and see if the answer matches. Fair enough. First part done. Second part. B1, show that the final temperature TF of the gas is 190 Kelvin. Now, notice one thing. In case of ideal gases, what is the definition of an ideal gas? They follow the proportionality between thermodynamic temperature and product of pressure and volume. You know the thermodynamic temperature is directly proportional to the product of pressure and volume. Okay, so you know that. Therefore, with the same ideal gas, same mole or same number of molecules of any ideal gas, if I do whatever to it, increase the temperature, decrease the pressure, increase the volume, whatever I do, temperature will still be proportional to my pressure and volume product, right? So you know that. Therefore, my T1 initial temperature is equals to my initial temperature is equal to the product of initial pressure and volume, right? Divided by my final temperature is also equal to my product of new pressure and new volume, right? So, I'm dividing the proportionalities. T1 is proportional to P1, V1 divided by T2 is proportional to P2 and V2. Whatever constants there are in between. So if there was a constant over here and a constant over here, it gets cancelled off. Fair enough. So using this ratio, what you can do is you can find out your final temperature because you know your final pressure and final volume as given in this box. So using the ratio, you can find out your final thermodynamic temperature, right? So your T2 is going to be 187.2 Kelvin, right? And your final answer, you're going to write it as 190 Kelvin in 2 significant figures because most of the cases, they've given the answers the data's in 2SF, right? So write the answer in 2SF over here. Fair enough. That is your answer to what? Part B2. Great. Now, sorry, part B1. Now, part B2, what does it say? The average translational kinetic energy, EK, of a molecule of an ideal gas is given by EK, or kinetic energy of any particle, is equals to 3 by 2 kT. So you probably know this from the ideal gas kinetic energy derivation, right? You should know it from that chapter already. This is the kinetic energy of any ideal gas particle or molecule. Okay, this is not the total kinetic energy of the entire system. This is the kinetic energy of any single molecule or particle, right? Now, don't get confused by translational kinetic energy. There are two types of kinetic energy as far as I remember, rotational and translational. Translational is when you move from one place to another. Rotational is when you rotate about one axis. So you probably might have read this in the book. But in case of rotational kinetic energy, it's basically they are usually diatomic molecules. So they rotate about an axis. In this case, they have specified it's a translational kinetic energy. And whether or not it is, it's not going to matter, right? It's not going to matter. What you are going to care about is the kinetic energy, right? So they're giving you the formula of kinetic energy of one particle. Now move on and see what the next part is saying. Where T is the thermodynamic temperature and K is the Boltzmann constant, calculate the increase in internal energy del U of the gas. Okay. Now, in case of del U, how do you find out the change in internal energy of the system? How do you do that? Change in internal energy is the sum of thermal energy provided in or taken out plus work done on the system or work done by the gas, right? Now, over here, what do you know? You know, initially, no amount of thermal energy was given in or taken out. So del Q, thermal energy change, is 0. So plug that in. This is 0. The amount of work done though, is it 0? No. Why? Notice one thing. Over here, expansion has taken place. 3.1, 6.3. The volume has expanded, right? Now, the other thing to note is, even if you didn't know that, you can see the temperature has actually decreased. Therefore, some amount of change in internal energy has taken place. And you know, since the temperature has decreased, your internal energy must have decreased, right? Your internal energy must have decreased. This can also be deduced by seeing my volume has increased. That means work is done by the gas on the system. So energy was lost by the gas. So if I take all those information, I can say, since del Q is 0, I need to find out the value of work done by the gas. Work done by the gas on the system. And I also know over here, since del Q is 0, I can directly write del U is minus work done, right? It's going to be minus work done. Now, the thing over here is, in case of decrease in internal energy or increase in internal energy, why would the internal energy of a system increase or decrease? The only reason is change in temperature, right? Change in temperature can only cause increase or decrease in internal energy. In this case, we do see a decrease in internal energy. And that is due to the fact that temperature has decreased. That means that the gas molecules have lost its kinetic energy. Therefore, that translational kinetic energy was changed into work being done on the system, right? So now to find this amount of work done or this change in internal energy, I can directly use this formula. Why? Because I know whatever kinetic energy of the system was lost was transferred into work being done on the system. So actually, your W is equals to 3 by 2 kT. Because that change in temperature, what do you know about temperature though from the temperature topic? Temperature is nothing but how much kinetic energy a particle has or a system has, right? Only due to that factor will temperature increase or decrease. If the particles have greater amount of kinetic energy, that means the amount of temperature, the value of temperature will increase, right? So knowing that, I can say, so since the temperature has decreased, I can say that decrease in temperature or decrease in kinetic energy was transferred into work being done on the system. So I can write del U is 3 by 2 kT, right? Del U is 3 by 2 times K Boltzmann constant times change in temperature is 100. Now this minus sign, I've added it over here, so I'm not adding it over here. Now I'm also going to multiply with 6.6 into 10 to the power 23 number of atoms. Why? Because remember, initially when I started reading this question, I mentioned this is the kinetic energy of one particle, of one molecule. So you need to multiply that with what? The number of particles to understand the kinetic energy of the entire system, right? This is giving you the kinetic energy of one particle or one molecule. Now to understand or to deduce the total kinetic energy of the system, you will multiply that with the number of particles in the system. That is, we figured out in part A that the number of particles is actually 6.6 into 10 to the power 23. So multiply this kinetic energy with that, this loss of kinetic energy with that, and you're going to find the change in internal energy. That is going to be 1400. So you're losing 1400 joules of energy. Why? Because kinetic energy was transferred into work being done on the system, right? And the other thing I want to mention over here is in case of change in internal energy, for ideal gases, what happens is we consider the potential energy between two particles or multiple particles to be zero. So if the internal energy is changing, it will only be due to the fact that your kinetic energy of the particles are changing, right? So if internal energy is changing, that means kinetic energy of the ideal gases are changing. And you can also say, since the temperature is changing, kinetic energy is changing, or the other way around. Since kinetic energy is changing, your temperature is going to change. Because what do you know about temperature? Temperature is the measure of kinetic energy of the system, nothing else, right? So what do you understand from this question? A, that change in internal energy is only due to the fact, in case of ideal gases, is only due to the fact of changing kinetic energy. And that can be figured out by your change in temperature. Great. So that is what we understand from this question. Fair enough. And don't forget to multiply 6.6 into 10 to the power 23, because without that, what you will be getting is the change in energy of one particle, not of the entire system, right? Fair enough. Now for part C, they're saying use the first law of thermodynamics to explain why the external work W done on the gas during expansion is equal to the increase in internal energy in B2. So your increase in internal energy is minus 1400, right? Negative sign because it's not exactly an increase, it's a decrease, but in terms of increase, it's going to be negative because in reality, it's decreasing. Anyways, they're asking use first law of dynamics to explain why external work done is equal to why the W, external work done, is equal to the change in internal energy. Very simple. The logic is as explained above over here, that since your thermal energy transfer is 0, that is, your Q is 0, no heat is transferred, right? No heat is given in, no heat is taken out. Therefore, del U has to be equal to the external amount of work done, or the work done by the system or by the gas on the system, right? Therefore, the only way your internal energy can decrease is going to be by the fact that work was done on the system, right? So that is only how your internal energy will change. So that is exactly what you're going to say over here. First thing you say is your change in thermal energy, 0. Therefore, your change in internal energy will be contributed by the fact that work was being done by the gas on the system. Great. So that is your question 1. Okay, so now question 2. This is from 970241MJ 2023. This is part B of some question, and it's saying an ideal gas has amount of substance N mole of substance, and the gas is initially in state X. In state X, it has pressure 2B and volume V. The gas is then cooled at constant volume to state Y with pressure P. The gas is then heated at constant pressure to state Z with volume 2V. Finally, the gas returns at constant temperature to state X. Okay. Part 1. Determine an expression for the temperature of the gas in state X in terms of N, P, and V. Identify any other symbol that you use. You know the formula, PV is equals to nRT. So plug in the variables over there. That is, your pressure is 2P. 2P, volume is V. N is N, amount of substance. R is going to be your your gas constant. And you make temperature the subject by taking N and R on this side of the equation, and you're going to have the expression for temperature. Great. So any other symbol, it is going to be basically R. Gas constant, you're going to mention that, and you're going to get 2 marks. Fair enough. Now, part 2, on figure 4.1, sketch the variation with the volume of pressure of the gas as the gas undergoes 3 changes. The state X is labeled. Label states Y and Z. Now, I have in short written what happens. I mean, what the pressure and volume is at each state. So let's understand what's happening from X to Y. X to Y. At X, notice your pressure is 2P, and at X, your volume is what? V. Keep that in mind. Now it's changing into Y. It's changing into Y. The gas is cooled at constant volume. Therefore, it's going to stay at V. It's going to stay where? It's going to stay at V on the x-axis because cooled at constant volume to state Y with pressure P. Therefore, volume stays constant, but your pressure decreases to where? To P. Right? P and V. Right. So this is going to be your X to Y transition. Now next, let's look what's going to happen from Y to Z. Great. So from Y to Z, the gas is then heated at constant pressure to state Z with volume to V. Therefore, your Y value now is going to be constant because the pressure is constant. Therefore, while keeping the pressure constant, you're going to increase the volume. Constant pressure with volume 2V. Pressure is kept constant. The system is heated such that the system expands, right? Therefore, to what volume? 2V. So while the pressure stays constant, increase to 2V. Great. Now from Z to X, what's going to happen? At this point, Z, the gas returns at constant temperature to state X. Remember, T is proportional to PV. Now, if you draw a graph of XY, you're going to notice that, so basically P is proportional to 1 by V. So what you're going to notice in that case is when the temperature is constant, this is constant, right? This is going to be constant. That basically means that you're going to have a 1 by X curve. And you're going to have a shape similar to this. Because over here, the increase in pressure is going to be inversely proportional to the volume. Okay? Your pressure is inversely proportional to the volume because your temperature is constant. Fair enough. So I can say P is proportional to 1 by V. So this is going to be your graph. Okay? So from Z to X, it is happening at constant temperature, which is why you get this shape of graph. Fair enough. So once you have drawn all the state changes, move on to the next question, where the problem really begins. So part 3, during the change of state from Y to Z, what's happening at Y to Z? And let me bring it in one screen. Right. So state change from Y to Z, the increase in internal energy of the gas is U. Remember, del U is equals to thermal energy transferred plus work done. So they're telling you from Y to Z, this transition, what's actually happening is the internal energy is increasing by a value U. So they've already provided that value in the chart. Now next, let's see what's happening. This part is done. This part. During the change of state from Z to X, from where to where? Z to X. From Z to X, the work done on the gas is W. Right. Therefore, since this transition is not happening at constant pressure, you cannot use the formula P times del V to find the work done. However, you know the amount of work done will actually be from from Z to X is going to be the area under the graph. This area under the graph denotes the amount of work done on the system because this is your P times V value. But since your pressure is not constant, you have to understand that the area under the graph is actually the work done on the system. So the volume decreases at constant temperature. Therefore, work is being done on the system. Great. Okay, so they've given you the amount of work done on the system while changing from Z to X. Okay. Complete table 4.1 to indicate for each of the 3 changes of state, the increase in internal energy of the gas, the thermal energy transferred to the gas, and the work done on the gas in terms of P, V, U, and W. Now, let's understand how to tackle this question. You know, from Z to X, since the change is happening at constant temperature, the change in internal energy is going to be 0. The change in internal energy from Z to X, is actually 0. Why? Because there's no change in temperature. And you know del U is going to be, there's going to be a del U or change in internal energy only when there's a change in temperature. Otherwise, there's no change in internal energy of any system. Granted, you know that. You can directly say that from Z to X, where is Z to X? Your change in internal energy is what? 0. Great. So your change in internal energy is 0 from Z to X. So del U is equals to Q plus W. You can say, since my change in internal energy is 0, Q I don't know, I know the W, the work done, which they've given is positive W. So I can say my Q is going to be minus W. So make Q the subject, and you're going to see that the thermal energy transferred to the system is minus W. Great. So you've finished this row. You know what's happening from Z to X. From Z to X, no change in internal energy. Great. However, now notice one thing. If from Z to X, del U is 0, the increase in internal energy, the decrease in internal energy that happened over here, that is, your pressure was decreased at constant volume. Notice one thing over here. From state X to P and volume V, it decreases to what? It decreases to P, pressure, and volume V. So what has happened? Your pressure has decreased at constant volume. Great. So if your pressure has decreased, what do you know over here? There is some amount of change in internal energy in this case. There will be some amount of internal energy in this case, but you cannot figure out exactly how much. You cannot exactly find out what the amount of change in internal energy is in this case. However, they've given you one value though. The value is from Y to Z, the change in internal energy is positive U. You don't know what the change in internal energy is over here. What is del U? I don't know. However, one thing I know is from Z to X, the change in internal energy is 0. So what's going to be my change in internal energy from Y to X? They've given you that. They have given you that. That is, del U is U. Positive U. Positive U. So the first thing you're going to do over here is write down all the change in internal energy at every change of state. Not change of state, but change of change in state. So in every case, list down what the change in state is, right? From X to Y, you don't know that. You don't know what's happening. You don't know what the change in internal energy is. From Y to Z, you know that is positive del U. From Z to X, again, you know, which is 0 because constant temperature. So what can you deduce from all over here? You can deduce that for the gas to come back at the same state X with the same temperature, it needs to have the same internal energy. At this point, the internal energy has to be the same. Therefore, from X to Y, whatever change had happened, it needs to be recovered by Y to Z because there's no change in internal energy between Z and X. Therefore, what I'm telling you is from X to Y, change in internal energy plus Y to Z, change in internal energy has to be 0. Has to be 0. So you can also add Zx. But you know this value, this change in internal energy is 0 because no change in temperature. Therefore, I can cancel this out. So now you know that the internal energy change from X to Y has to be what? Has to be negative U. because otherwise it cannot come back to the same state as of x. It cannot, because at x it needs to have the same amount of internal energy. Now you know from y to z there is a positive gain of internal energy. However, until and unless you lose the same amount of internal energy from x to y, you cannot gain plus u and come back to the same internal energy, because the overall change in internal energy has to be 0. So let's see now, minus u plus u plus 0, is it 0? Yes, it is. This is going to be cancelled off and you're left with 0. So whatever gain of internal energy happened from y to x, the same decrease had happened from x to y. Otherwise, the internal energy cannot come back to the same amount at x. Therefore, you know the change in internal energy from x to y. What is it? Minus u. So what do you know? You know this value, this value, this value, and this value. You need to figure out these few values now. Okay. Now, let's make it easier. From x to y, is there any change in volume? No. From x to y, notice constant volume. Therefore, will there be any work done? No. No work will be done. Therefore, again, del u is equals to q plus w. Now, in case of del u, what is the change in internal energy? What did we figure out? Minus u. Minus u. So, plug minus u. Is there any change in work done? No. 0, because constant volume. So, what is your change in thermal energy going to be? Minus u. Therefore, your change in thermal energy is minus u, while your work done is 0. So, now you know this value and this value as well. So, you're only left with one column, that is from y to z. Great. So, let's see y to z, what's happening. I need to find out the change in thermal energy and the work done. Now, the work done part is very easy. Why? Because the area under the graph, or the amount of work done, is basically pressure times change in volume. Your pressure from y to x is what? Constant. And your change in volume is V, is 2V minus V, which is V. So P times V is your work done on the system. And this is going to be negative. Why, you ask? Because volume is increasing. Work is done by the system, not on the system. Since volume is increasing, negative PV. Great. So I know the work done on the system. Now again, use the same formula. Del U is equals to Q plus work done. What do I know about the work done? Minus PV. What do I know about the change in internal energy? Plus or positive U. U. So what is the thermal energy provided to the system going to be? PV plus U. U plus PV. And that is how you're going to solve this question. Usually what I see is they give really tough questions for these, thermodynamics questions. That is any sort of state change, pressure change, volume change. In these cases, when you have to draw the graph and analyze what the change of internal energy is, it gets really tricky, right? So you need to be careful. You need to solve a couple of questions. You can solve the ones in this video on your own and try it and see if you can do it. So now question 3, state the first law of thermodynamics. Identify the meaning of any symbols that you use. So del U is equals to plus work done plus thermal energy transferred. U is increase in internal energy. W is work done on the system. Q is energy transferred to the system. And make sure you give the right signs. Okay, now part B. Just the state of an ideal gas is continuously changed according to the cycle ABCDA shown. Okay, so it's going from this. At this point, it has a certain internal energy U. It is going to B at constant pressure. It is going to C at constant volume. It is going to D at constant pressure, but greater amount of pressure, and is coming back to A at constant volume and getting to the same internal energy value. Therefore, overall, through the entire circle, it comes back to the same internal energy. Keep that in mind. Now, for part 1, complete the 3.1 table 3.1 for the changes A to B and B to C by placing 2 ticks in each row. This is from, by the way, 97242 MJ23. So, they're asking you to denote what's happening from A to B and B to C in terms of change in internal energy and change in work done. So, before I explain this, I'm going to explain the change in work done. So, for A to B, notice what's happening. At constant pressure, your volume is decreasing. Volume is decreasing means there's external amount of work done on the system. Therefore, you're decreasing, let's say, if this was your piston, you're decreasing the volume. That means you're doing external work on the system. Therefore, this del V volume times P is going to be positive work done on the system. So, positive work done. And from B to C, notice the volume is constant. Pressure increases, but change in volume is 0. So, P times 0 is always 0. So, work done on gas, 0. Now, this is where most people got stuck. What's happening from A to B? If I write, to the internal energy. What's happening to the internal energy from A to B? If I write the equation, then U is equals to Q plus work done. You know, from A to B, work done is positive. A to B, work done is positive. And you know the change in state is being at constant pressure and the volume is decreasing. And now any normal individual would go ahead and take increase. Why? Because work done is increasing. Therefore, the internal energy is supposed to increase, right? However, no. You forgot about the variable Q. There is also another variable Q, thermal energy. And in this question, nowhere have they mentioned what's happening to the thermal energy. Is it being transferred? Is it being withdrawn from the system? Which is why you have to do something peculiar. That is, take the help of del U is equals to 3 by 2 K into T. Now, how do you use that? Notice one thing. Your internal energy only changes if your if your temperature changes. Internal energy will not change if your temperature is constant. And in a pressure versus volume graph, if your temperature is constant, the change will be like a curve, like in the previous question over here. Like over here, from Z to X. If temperature is constant, it's going to be a graph similar to Z to X. But temperature is not constant over here. What is happening to the temperature over here from A to B? Using that, I can predict what the change in internal energy is, because I don't know what the value of thermal energy is. Is it being withdrawn? Is it being given into the system? I don't know. So I need to take the help of temperature. So what is happening from A to B? What is happening is, let me show you something. From Charles' law, if you notice, this change in volume, or this green highlighted area, notice the change in volume, Vd to Vc. Okay, what is happening is you're decreasing the volume from Vc to Vd. Great. And you're doing that at constant pressure. You're doing that at constant pressure. Now notice one thing. This point has temperature 600 Kelvin. And this point has temperature of 400 Kelvin. Therefore, when you're decreasing the volume, when you decrease the volume del V from Vc to Vd at constant pressure P, your temperature also decreases. Your temperature also decreases. And you can also deduce that from this formula, or from this proportionality from ideal gas, that P is proportional to the product of pressure and volume. Since your volume is decreasing, your temperature is also decreasing. Therefore, you have to say that in this case, since your temperature is decreasing over here, your change in internal energy is negative, meaning decreases. Your internal energy decreases, not increase. Because in this case, what's going to happen is thermal energy is actually going out of the system, negative Q, which is why overall, overall value of del U is negative. Since you don't know the value of del Q or change in thermal energy, you have to take the help of your T is proportional to product of pressure and volume. Great. Now B to C is easy again. What's happening from B to C? B to C, if I write del U is equals to positive Q plus work done, is there any work done over here? Look, because volume is zero. Volume is constant. No change in volume, right? Del V is 0. However, notice one thing. Pressure is increasing. So if I'm not increasing the volume, how am I increasing the pressure? I'm increasing the pressure by adding thermal energy to the system, right? The pressure could have been increased by changing the volume as well, by decreasing the volume, right? However, in this case, no work done. Therefore, the change in pressure is due to the fact that you're adding thermal energy to the system. Since you're adding thermal energy to the system, that means there is a gain in internal energy, hence positive change in internal energy, hence increase in internal energy, right? Therefore, this is going to be your answer for B part 1. Okay. Now, for part 2, use the first law of thermodynamics to describe and explain the energy transfers associated with one complete cycle of ABCDA. Okay, so that is our graph ABCDA. So to answer it, we can say, we know the work done on a system is P times del V. From C to D, more work done by gas. From C to D, more work done by gas. Notice the area under the graph. More work done by gas. That is, since the volume is increasing, work is done by the gas. Great. More work done by gas from C to D. And from A to B, less work done on gas. On gas. Because over here, your volume is decreasing. Your volume is decreasing. Therefore, work is done on the system, on the gas. Hence, over here, the, work done is positive. And from C to D, work done was negative. Over here, positive. However, notice that the work done from C to D is larger than the work done on A to B. Why? Because notice the area under the graph. The pressure is higher over here and pressure is lower over here. So keep that in mind. Therefore, A to B, less work done on gas. B, C, and D, A, no work done by or on gas. Notice B, C, and D, A, there is no amount of work being done over here. Work done over there is 0. Great. In one cycle, no net change in internal energy. We know for this to come back to state A, there should be no change in internal energy. Because at this point of pressure, of this pressure, and of this volume, T is proportional to PV, it has a certain temperature. At this point of pressure and volume, it has a certain temperature. So, if the temperature is constant, you can never have a different internal energy. So, as it goes around through A, B, C, D, A and comes back to A, it's supposed to have the same internal energy. But what we saw is from C to D, greater amount of work done by the gas, and A to B, less amount of work done on the gas. And from B to C and D to A, no work was done. Therefore, we can conclude, since no net change is supposed to happen in one cycle of internal energy, to compensate for the extra work done by gas, thermal energy must have been added to the system. Thermal energy must have been added to the system. Therefore, we know over here, for example, B to C, thermal energy must have been added over here. Otherwise, greater amount of work done by the gas would not be possible. We wouldn't be able to balance the equation, right? In the sense that from here to here to here to here, if no amount of thermal energy was provided over here, it would have less internal energy, negative internal energy compared to its initial internal energy at A, because less amount of work done was done on A to B, and more amount of work done was done by the gas from C to D. So energy is actually lost. Therefore, thermal energy must have been provided from B to C, or through the entire cycle, that is. Otherwise, it's not possible, right? Therefore, Q, or thermal energy, must have been provided to the system. Right. Fair enough. This was a pretty complicated question, both this part and answering this part. So you need to have really good concept over here of change in thermal energy. You need to have a good idea of all these graphs: Boyle's law, Charles' law, and pressure law. Okay? Fair enough. So that is going to be the 3 questions for this video, and see you in the next one.